Hey everyone, Mr. Houck here. In today's video, we're going to be looking at ellipses. By the end of this video, we should be able to derive the equation for an ellipse and identify characteristics of ellipses. Let's go ahead and get started here. So, recall previously that a conic section is an intersection of a plane and a double-napped cone. And we saw previously that if we slice a cone with a plane that is parallel to the base of the cone, that we get a circle. And you can see that here in this very first image. Plane is parallel to the base of the cone. When we slice through, we get a circle. But what would happen if the plane is not parallel to the base of the cone? Well, the answer is we would get something called an ellipse. And consider this image to the right of the circle image. Again, we have a double-napped cone, but notice that this time the plane that we're slicing with is no longer parallel to the base of the cone. Okay, it's at an angle. So we end up creating an ellipse. Now, unfortunately for us, when we're dealing with circles, it was easy for us to derive the equation for a circle because of the fact that the distance between the center of the circle and any point on the outside of the circle was always the same. Ellipses don't share that common trait with circles, so deriving the equation of an ellipse is going to be more difficult. But the way that we're going to do it is we're going to begin by considering a very simple circle. And the circle that we're going to consider is the circle centered at the origin with a radius of 1. And here's the equation for that circle. So basically, to make this circle an ellipse, we're going to either need to stretch it in the x direction horizontally, stretch it in the y direction vertically, or stretch it in both directions. And we're going to do this by kind of looking at each case, and then we're going to look at what happens when we stretch in both directions. Okay? So first, let's think about stretching the circle horizontally in the x direction. Essentially, what we would have to do is we'd have to scale all of the x's by a factor of some number, and we'll call this number a. We'll call it the scale factor of a. In order to scale in the x direction by a factor of a, what we're going to have to do is we're going to have to divide all of the x coordinates by a. So what that means is we're going to be turning all the x's into x over a's. So we're going to take our circle equation right here, x squared plus y squared equals 1, and we're going to replace the x with an x over a. Distributing the power of 2 to both the numerator and the denominator, we get x squared over a squared plus y squared equals 1. So seeing kind of a more concrete example, let's look at one with some actual numbers. So here in this picture in red, this is the circle centered at the origin with a radius of 1. And what we did is we elongated it in the x direction horizontally by a scale factor of 2. And the way we did that is we took the x and we replaced it with x over 2. So we put x over 2 in parentheses, and we get x over 2 squared plus y squared equals 1. And if you go and graph that in Desmos or some kind of graphing calculator, this is the ellipse that ends up getting created. And notice it just stretched the x coordinates by a factor of 2. Let's now do the same thing with the y coordinates. So in order to elongate the circle in the y direction, we have to do the same thing, but with the y coordinates. We're going to scale it by some kind of factor. We already used a, so this time I'm going to use b. So essentially what we're going to do is we're going to take our circle equation, x squared plus y squared equals 1. That's, the circle centered at the origin with a radius of 1. And we're going to replace the y coordinate with y over b. So that's what happened right here. Y got replaced with y over b. And after, again, distributing the power of 2 to the numerator and the denominator, we get x squared plus y squared over b squared equals 1. Now, again, looking at a more concrete example, here is once more that very simple circle centered at the origin, radius of 1. And notice that this ellipse, this horizontally stretched ellipse, has this as the equation. X squared plus a y over 2 squared equals 1. And notice that it is simply stretching vertically by a scale factor of 2. Okay? Now, as mentioned earlier, we can elongate circles in both the x direction and the y direction. We would just have to pick a scale factor a and a scale factor b for each x and y direction that we want to stretch by, and plug it into that simple circle equation we've been referencing. Okay. Now, this particular equation if A is bigger than B, would give us a horizontal ellipse centered at the origin. So, not every ellipse that we're going to work with is going to be centered at the origin. And when I said it's a horizontal ellipse, that means it is wider than it is tall. Again, that's if A is bigger than B. So let's start thinking about ellipses in general. In addition to defining an ellipse as a curve created by the intersection of a plane and a cone at a certain angle, we can also define an ellipse as the set of all points, x, y, such that the sum of their distances from two fixed points is constant. Each of these fixed points is called a focus of the ellipse. Now, I know just kind of looking at that description, that definition of an ellipse, can be kind of confusing. So let's actually look at an animation to get an idea of what this means. And I put the link to it right here. If you're online, you can click on that link. It'll take you to an interactive geometry template, and it'll let you kind of play around with an ellipse. So let's go ahead and pull that up. All right, so I have that right here. And notice we have an ellipse, and these points right here, F1 and F2, are the two foci. That's plural for focus. And what I want you to notice is the numbers up top. So we have a point P. Notice I'm moving this point P around. And we have the distance. We have point PF1 is the distance from P to F1. And PF2 is the distance from P to F2, of course. Now notice where it says PF1 plus PF2 equals 16. No matter where I drag this point, the individual line segments might differ, but the sum of those two line segments is always going to be 16. That's what defines an ellipse. It's the all the possible p's, all the possible point p's, or all the xy coordinates, such that these two distances, their sum is always constant. Okay? So let's look at some of the vocabulary we're going to have to be very familiar with for this unit when it comes to ellipses. Every ellipse will have two axes of symmetry. The longer axis is called the major axis, which is right here, and the smaller axis is called the minor axis. Notice that the major axis and the minor axis, they intersect perpendicular to each other at the center. Now the foci, which again is the plural focus, will always be located on the major axis. So whichever one is the longest axis will also have the foci. Each endpoint of the major axis is called a vertex. So on the major axis, the endpoints are called the vertices. And each endpoint on the minor axis, or the smaller axis, are called the covertices. Now, just like with circles, we have a general form of an ellipse. So in general, an ellipse has the equation ax squared plus by squared plus dx plus ey plus f equals 0. This is different from a circle because a circle, the coefficients for x squared and y squared were always 1. Okay? So in general form, you can tell a circle apart from an ellipse based off of the fact that x squared and y squared have coefficients other than 1. Now, much like with circles, however, we typically want to express the ellipses in standard form. So now let's look at the standard form equations for both horizontal and vertical ellipses, starting with horizontal. So for horizontal ellipses, again, notice that the major axis is running horizontally, the minor axis is running vertically. If we take a closer look at this, so here's the center of our ellipse, HK, just like the center of ellipse, or the center of a circle we called HK, the center of the ellipse we'll call HK as well. Now the distance, and I'm going to label some of this stuff here, the distance from the center to the foci on either side we call C. The distance from the center to a covertice, or to the covertex, we're going to call B. And the distance, let me see if I don't want to overwrite the C that we have there, but the distance from the center to the main vertex, or just the vertex, we call A. So I'll do this. Let's make this easy on ourselves. Call that chunk A. Okay? So here's the general formula of a horizontal ellipse. We have x minus h squared over a squared plus y minus k squared over b squared equals 1. And again, hk is going to be the center of the ellipse, just like hk was the center of our circle. A, again, is the distance from the center all the way to a vertex. B is the distance from the center to a co-vertex. And C is the distance from the center to a focus. Now, this is the formula. And again, A is always going to be greater than B. So notice that if A is greater than B, then A squared is also going to be bigger than B squared. So when the largest number is underneath the x variable, we have a horizontal ellipse. It's going to be different for a vertical ellipse. Notice for a vertical ellipse, again, if A is bigger than B, notice that A being bigger than B means the largest number is underneath the y variable. So depending on where the largest denominator is, that's going to determine whether we have a horizontal ellipse or a vertical ellipse. So again, looking at our horizontal ellipse, the length of the major axis, well, if half of the major axis is A, then the entire major axis, the length of it, is 2 times A. Similarly here, if the length of half of the minor axis is B, then the length of the entire minor axis is 2 times B. The coordinates of the vertices, we can see are h plus A, comma k, and h minus A, comma k. So again, all we're doing here is we're taking h being the x-coordinate of the center, we're adding in the distance between the center and the vertex, and that gives us the coordinate for the vertex. Similarly, for the minor axis, from center to a co-vertex, if that distance is b, then the coordinates for the co-vertices are h, comma k plus b, and h, comma k minus b. So that's what we have right down here. Lastly, we look at the coordinates of the foci. The coordinates of the foci are going to be h plus or minus c, comma k. So here's one of them. Here's the h plus c, comma k. Then here's the h minus c, comma k. Notice that the way that we're writing these, this h plus or minus, k plus or minus, this plus or minus business that we have going on, means that there are 2 different coordinates. We're going to have one where it's h plus a, comma k, in this case. Then we have another one where it's h minus a, comma k. Okay? Now, one thing that I want to write in here, I forgot to actually write this out in the notes, is how you can calculate c. So c, it turns out we can calculate because c squared is equal to a squared minus b squared. Well, if c squared is equal to a squared minus b squared, and I take the square root of both sides, then this means that c is the square root of a squared minus b squared. Okay, so that's a quick way that we can calculate c. And again, remember that c is the distance from the center to the focus. Now, for a vertical ellipse, it's basically the same exact deal, except for now the major axis is vertical, the minor axis is horizontal. All this information tells us basically how to calculate the main parts. We can find the length of the major axis, length of the minor axis, the coordinates of the vertices, coordinates of the co-vertices, and the coordinates of the foci. And here in the notes, I just list out how we can calculate each one of those. Okay? So let's move on to something called eccentricity. Now remember how previously we mentioned that a circle is a special case of an ellipse. Well, this brings up a property called eccentricity. Eccentricity can be thought of as a measure of how circular or non-circular a curve, in this case an ellipse, actually is. And we will use lowercase e as the variable to define eccentricity, where e is c divided by a. So we're looking at the ratio between the distance between the center and the focus and the distance between the center and the vertex. it turns out that a circle is an ellipse that has an e-value and eccentricity of 0. And what that basically means is that if you have an eccentricity of 0, that means that the distance, the c, is a 0. So that's how a circle is a special case of an ellipse. Now, in general, the closer the eccentricity of an ellipse is to 0, the more circular that curve is. For ellipses, the eccentricity value will always be between 0 and 1. So let's try some examples. Okay. For these ellipses, we're going to be given an equation, and we want to find all the main characteristics and parts of the ellipse. So one thing that we just want to remember in general, let's remind ourselves that A is going to be bigger than B. A is always bigger than B. And let's go ahead and look at our first example. So for the ellipse given by this equation, we want to find all the following: the center, the vertices, the covertices, the foci, the eccentricity, the length of the major axis, and the length of the minor axis. We know that for a lot of these equations, we're going to need to know the A term, the B term, and the C term. So that's typically how I start these problems. So notice that this equation is in standard form. And in standard form, the bottom is A squared and B squared. And remember, since A is bigger than B, that means 64 is A squared, 49 is B squared. So let's go ahead and calculate A, B, and C. So A is going to be the square root of 64, which is 8. B is going to be the square root of 49, which is 7. And remember, we had a formula to calculate C. C is going to be the square root of A squared minus B squared. So that's going to be the square root of 64 minus 49, which is the square root of 15. All right, so with that information, we are now ready to go ahead and calculate some of this stuff here. And I'm going to break this off into sections just to give us some room and kind of keep it organized. All right, so let's first start by trying to find the center. So the center of an ellipse is h comma k. And if we think about the equation, well, remember it was x minus h. Let me write this out actually. X minus h squared over a squared plus y minus k squared over b squared equals 1. So h and k are the coordinates of the center. Remember, we have to change their signs because they have negative signs in front of them. So for looking at our equation here, we should have a center of -4, +6. One blue here. -4, +6. All right, so in standard form, center is very easy to pick out. Now let's look for the vertices. So the vertices, if we look back to that page that had the equations or the formulas of how to find all the different characteristics, the way that we find the vertices is for a, because this is a horizontal ellipse, by the way, horizontal because the A term, the largest number, is underneath the X. Okay, so since this is a horizontal ellipse, the vertices we find by doing H plus or minus A, comma K. Well, we know H is -4, we know K is 6, and we know A is 8. So H plus or minus A, that's going to be -4 plus or minus 8, comma K, and K is 6. So this would be, and remember this plus or minus sign means we have two different coordinates. So -4 plus 8, that's 4, 6. But we also have to calculate it with -4 minus 8, and -4 minus 8 is -12, comma 6. See, I like it when the box gets shaded in. There we go. All right, now let's look for the covertices. So again, since this is a horizontal ellipse, since the number underneath X is largest, The formula that finds the covertices is h comma k plus or minus b. And let's see, that's going to give us, well, h in this case is -4, k 6, plus or minus b, and we know that b is 7. So 6 plus or minus 7. And if we go ahead and apply that, that's -4, comma, we'll see 6 plus 7 is 13. Then we're going to do the same thing, -4, but this time 6 minus 7, which is -1. All right, so we get -4, 13, and -4, -1. Now let's move on to the foci. So for a horizontal ellipse, the foci can be calculated using h plus or minus c, comma k, and that's going to give us h is -4, plus or minus, let's see, c is square root of 15, comma k is 6. So because of the plus or minus sign, let's look at both coordinates. We're going to have -4 plus square root of 15, comma 6, and -4 minus square root of 15, comma 6. So those will be the two coordinates of our, or the coordinates of our two foci. Now let's look at eccentricity. Again, a measure of how circular or non-circular something is. So eccentricity is given by the equation E is equal to c divided by a. We know c is the square root of 15. We know a is 8. And let's just let's turn this into a decimal, because we looked at eccentricity as a range between 0 and 1. Well, square root of 15 divided by 8, if you plug it into a calculator, is about 0.484. And remember, we said the closer something is to 0, the more circular this curve is. All right, lastly, let's look at the length of the major axis and the length of the minor axis. So once again, I'm going to make a big point of it this time. This ellipse is horizontal. Horizontal. Okay, so the length of the major axis is going to be the horizontal axis of symmetry, which means that we're trying to calculate 2 times a. Well, we know a is 8, so it's just simply 2 times 8, which is 16. It's a length, so we'll say units. And then lastly, length of the minor axis. Minor axis is the vertical axis, so that'll be 2 times b. We know b is 7, so this will be 2 times 7, which is 14 units. All right, so it's a lot of things to calculate, but fortunately, it's all fairly easy calculations. So let's look at an example that takes the difficulty up a little bit now. This time, we're going to look at an ellipse, but given in general form, given the general equation. And what we're going to have to do in order to find all this nice information is we have to have the standard equation. Because if we look at the page before this, all this information, all these nice little formulas to calculate the different key characteristics of the ellipses only apply when we're looking at the general formula of the ellipse, or the general equation of the ellipse, rather. So how do you think we're going to convert from the general equation to the standard equation? Well, the answer is by completing the square. So let's go through our process of completing the square. First thing that I'm going to do is I'm going to go ahead and rewrite my equation. I'm going to start grouping the x variables and the y variables together. So we have 4x squared plus 8x plus 49y squared minus 98y. And I'm going to go ahead and take the constant negative 731. I'm going to move it to the other side of the equation by adding it. Okay. Next, we need to go ahead and look at our variables separately. So we're looking at 4x squared and 8x. However, we don't do completing the square unless the coefficient of the squared variable is a 1. But this is a 4, and this is a 49. So both the coefficients in front of the x and the y are both not 1. So we're going to need to do some factoring first. Out of the x variables, I'm going to factor a 4. I'm going to get x squared plus 2x. And I'm also going to leave a little bit of space because we know with completing the square, there's a constant that we need to add in. Now looking at the y variables, well, this 49 is being multiplied to y squared, so let's factor out the 49, and we get y squared minus 2y. And again, let's leave a little space there for the constant we're going to add in, equals 731. Let's think about these constants now. What constant can I add here to make this in the parentheses a perfect square? Well, if we take half of 2, we get 1. We square it, so 1 times 1, we get a positive 1. I don't need the plus sign twice. There we go, plus 1. Now, we can't just have this on the left side and not compensate for it on the right side. So since 1 is being multiplied by this 4 here, on the right side, we're going to add 4 times 1. Now let's look at this constant piece that we're going to add in. We take half of negative 2, which is negative 1. Negative 1 times itself gives us a positive 1. And when we go to compensate for it on the right side, this positive 1 is being multiplied by the 49 on the outside. So we're going to be adding 49 times 1. Okay. Now let's continue our completing the square process. So x squared plus 2x plus 1 right here, that's going to factor into x plus 1 times x plus 1. Y squared minus 2y plus 1 is going to factor into y minus 1 times y minus 1. And on the right side, if we go ahead and multiply and add all our terms together here, we end up getting 784. Continuing to simplify, this is now 4x plus 1 to the second power plus 49, y minus 1 to the second power equals 784. Now, almost done. There's one more thing we need to do though. If we look at the standard form for these ellipses, notice that the right side always has a constant equal to 1. This constant on the right side is a 784. So what we're going to do is we're going to divide both sides by 784 to force the right side to equal a 1. So here, then here, then here, here, and simplifying one last time now. 4 divided by 784, if you plug that into a calculator and simplify the fraction, you get x plus 1 squared over 196. So basically 4 over 784 was 1 over 196 plus 49 over 784 simplifies to 1 over 16. So this would be y minus 1 squared over 16 equals 1. And it seems like it was a lot of work there, but now we have our general equation for this ellipse represented in standard form. And that means we can now go about finding all these different key characteristics. Now again, to find all these key characteristics, we're going to need the a, the b, and the c terms. Now let's go ahead and dedicate some space and time to finding those. I'm going to give ourselves some space over here. Starting with the a term. Now first off, let's talk about how this ellipse is oriented. So this ellipse, because the largest denominator is with the x variable, this is a horizontal ellipse. So this ellipse is horizontal. That tells us which formulas we're going to be using. So let's start with the a term. A is going to be the square root of 196, which is 14. B is going to be the square root of 16, which is 4. And C is going to be the square root of a squared minus b squared, which in this case is 196 minus 16. That's going to be the square root of 180. 180 is 36 times 5. And 36 is a perfect square. So C is 6 square root of 5. Okay, so we have our A, B, and C term. Now we can go about finding all these different little key characteristics. All right, starting with the center. So again, this is a horizontal ellipse. It doesn't affect the center. So the center we know is the coordinates HK. Well, HK, we change the signs here, so this will be a -1, +1 for the center. Okay, nice and simple there. The vertices, since we have a horizontal ellipse, the vertices are going to be given by h plus or minus AK. This is going to be h is -1, plus or minus. We found a to be 14, and k is 1. So going through and doing some quick math here, that's going to give us the coordinates, let's see, -1 plus 14, that's 13, comma 1. And then -1 minus 14, that's going to be -15, comma 1. Covertices, that's going to be given by the formula h, comma k plus or minus b. In this case, that's going to be, we found h to be -1, k is +1, b is 4. So -1, comma 1 plus or minus 4. That's going to give us the vertices -1, comma 5. That's from the 1 plus 4. And -1, comma -3 from the 1 minus 4. Okay. Next, the foci. Again, for a horizontal ellipse, foci are going to be given by the formula h plus or minus c, comma k. In this case, that's going to end up being -1 plus or minus 6 squared of 5, because we found c was 6 squared of 5, comma 1. And our two coordinates for that are going to be -1 plus 6 squared of 5, comma 1, and -1 minus 6 squared of 5, comma 1. All right, eccentricity. C term divided by the A term. We found the C term was 6 squared of 5. A term is 14. Notice the numbers on the outside, pretty much the numbers not underneath the square roots. 6 and 14 can both be reduced with each other by a factor of 2, so we get 3 and 7. So this is really 3 squared of 5 over 7, which if we simplify that, is about 0.958. All right, then lastly, length of the major axis and length of the minor axis. Length of the major axis, since this is a horizontal ellipse, it's going to be 2 times A. A we found to be 14, so 2 times 14, which is 28 units. Okay, length of the minor axis, it's going to be 2 times B, since this is a horizontal ellipse. B we found to be 4, so 2 times 4, which is 8 units. All right, so a lot of work involved with that one. Remember, this was all one problem right here. We started by taking the general equation, converting it to standard form. From standard form, we can find the A term, the B term, and the C term, which allows us, with all the formulas that we have, to calculate all these little key parts of the ellipse.